that you weren't looking at the note guide that had that number on it, right? Okay, and then I need the velocity squared, so is it 2.6? Doesn't have the 6.644? Oh, I'm sorry.
What's the 1.602?
That's the electron charge, right? So 12 times 9e9 times divided by 6. And then be careful when you're doing this. Whoops. Really, if you're going to do this all in one swell foop like I'm doing, you need to put this in parentheses, right? Go divided by the entire denominator in parentheses. I forgot the parentheses, so I said divided by this, divided by this, divided by this, which is exactly the same thing. And what the devil? Oh, I forgot to square my e. There you go. Yeah, I'm getting that R is, and this is the correct answer, 1.234 times 10 to the minus 13th meters. Now to use the to use language is definitely dodgy, you know, for high school, right? Can you say that this alpha particle has penetrated the nucleus? No, why not? Why is this not anywhere near the nucleus? Is it that it's 100 times the nuclear diameter away from the center of the nucleus? Yeah, nuclei are on the order of 10 to the minus 15th. This thing is 100 times that farther away, and so it can see the nucleus. It's like the Death Star. That's no moon, you know, right? You know, it can see it, but it's like, oh, it flies away, right? It's like those. These problems are just like those things. I don't think we've had them. What's the little ASB fun thing where we have all the inflatable stuff in the gyms and people run around and all school barbecue. And we haven't done this for a while, but there's one where they tie a bungee cord onto you and you run. You run and you eventually stop moving. Your kinetic energy is converted into elastic potential, and then it like flings you head over teacups backwards. This is fun because everybody likes to be ripped off their feet by a very large rubber band and thrown backwards, head over tin cup, onto this soft surface, and have people laugh at you. It is fun. I've done it. It's like you're running, and it's like there's this overwhelming feeling of doom, though, when you come to a halt. You're like, oh no. Boom. Yeah, it's the Wile E. Coyote. You're like, this slash thingy. This guy? Is if you're on the calculator and you're going this times this times this divided by, and then you have to say all of that, right? Okay. So that's example problem number 1. Example problem 2 says, through what potential must you accelerate an alpha particle, right? So this adds possibly an extra feature. Instead of telling you the velocity here, we have to express that velocity in terms of accelerating potential and charge. Yes, doesn't that sound really difficult?
Yeah.
Yeah? So that adds another layer of difficulty, or does it? Or does it? Well, let's consider this problem, right? Let's consider this problem in a different way. Let's consider it in terms of, let's roll marbles. I'm going to use marbles here. I'm not going to say balls. Okay? Let's roll marbles down an inclined plane. This represents, gentlemen, this represents, the height of this ramp represents the voltage that we're accelerating these particles through. Yes? Hello? Making an analogy here. I'm not going to say risque words, though. I'm not this time. Right? So the height of this ramp represents, height here is like voltage, right? Okay? So we're rolling it. This is our accelerating region. We're going to accelerate it through a voltage. This is like voltage. Yes? Okay? They roll down here. Now, as they approach the nucleus, they approach this 1 over r thing. And then of course, how do you like actually penetrate the nucleus? Well, you get close enough that the strong nuclear force says, I like these things, and grabs onto it. It's like the tractor beam for the Death Star. See, Star Wars rules, right? Okay? That's a trap. Okay, so basically, this is the Coulombic repulsion. It's like more and more and more energy. But if you get close enough, the nucleus goes, "Oh, I like that." Ka-chunk. Yeah, right. That's what's going on there. Okay, so let's take a look at this. Right? Any guesses? This is a particular voltage. Yes. Any guesses how high that ramp needs to be so that the marbles make it over this? The limit is equal, right? And then the answer is a little bit higher, right? Or something like that, right? But so the limit is that it's exactly the same height. Okay? So when they give you these questions, through what potential must you accelerate it to get this close to an atom, aren't they just asking you what is the voltage that distance from the atom? Yeah. Yes, they are. They're just asking you they're asking you the height of this ramp, which is the same as that height. This is really easy. Isn't voltage kq over r? Yes, it is. Okay, so let's just solve it that way, right? For this guy, out of analogy mode into math mode, right? This is going to be kq over r. So this is your second example. The accelerating voltage is simply going to be, and I could show it mathematically, but typically kids don't like that as much. They like the marble rolling analogy. All you do, by the way, is you say V2E. Mathematically, this is what happens, right? The middle doesn't matter anymore. We don't care what speed it's going, right? And doesn't the 2E cancel out? So that the voltage at that close to the nucleus is the same as the accelerating voltage. I mean, that's mathematically what goes on there. So 99, and then what is a uranium nucleus has how many protons? Well, that's what Z is. Z is atomic number in physics land. So it's 92 electron charges, right? So 92 times 1.602 E minus 19th coulombs, right? And then 7.4 femtometers, right, is 7.4 times 10 to the minus 15th meters, right? What is 10 to the minus 12th? Femtometers. Yeah? 10 to the minus 12th is what? Come on. 10 to the minus 9th is what? Nano. 10 to the minus 6th is micro. 10 to the minus 3rd is milli. 10 to the minus 12th is pico. So 10 to the minus 12th booze is picobooze. Yeah? And 7.4 times 10 to the minus 15th meters is 7.4 femtometers. I just did that so I could say femtometers in a strange way. Femto, F-E-M-P-T-O. Yes, sir.
I have a question. Why aren't we, I know we can't tell where exactly the electron is, but why doesn't it matter? I know that it's moving around the nucleus at every second, but wouldn't it change at least slightly?
Oh, I see. So why doesn't this analysis take into account the electrons flying around? Because they're so small. They're inconsequential. Right? It's like, yeah, they do. Oh, I see.
Why doesn't that matter?
Yeah, for this potential. And I guess that's because they're smeared out in space. You always solve these as if you're ignoring the electrons. And that is a good question, right? But I guess because you're in that 100,000 times, you're inside the atom itself, right? So the electrons are around you when this happens.
Why do you have the 90 alpha beside this?
That's the Z. Z is 90.
So you get 92.
It's 92 electron charges. Yeah. Okay, very unhelpful. My calculator gives me this very large number, which, by the way, is about 17.9 times 10 to the 6th volts. Okay, and it would take me, 15 seconds operating quickly to get that into scientific notation, but that's what it ends up being. Yeah? Are we good? Do you guys want to try one of those? 18.
Whiteboard.
Whiteboard.